Alright, so in our last video, we found the packed bytes buffer and we wrote our own unpacking code in Rust. And we unpacked it, we mapped it into Binary Ninja. First, we added it into the file by appending it to the end of the file, which does not affect the PE format because, as you may have noticed when we were writing our PE loader in the initial challenges, the sections and segments of the PE format are defined in the headers. So they have the pointer to the sections and the size. So since you have the address of them and the sizes of them, and you pass it from like top down that way, any data that's appended to the end of the file is not going to be read from at all from a PE loader. It's going to be ignored. Now, it does affect the hash of the file. So we were able to unpack the packed bytes and append that to the end of the file and map it in as a section in Binary Ninja so that those bytes have an associated virtual start address and end address. Added a cross-reference that to some packed bytes, and we have that code, right? If I go to unpacked here, this is the unpacked code now. And if I click the unpacked entry point main, you see it's got a code cross-reference to some packed bytes here. So that was cool. Now we did that just by looking at the unpacking routine, right? Understanding it and writing our own version of this in Rust to get the proper code and load that in. Now there are so many different ways that you can do this. You can get the unpacked code. This was just one of the ways. Really, it comes down to creativity. And the more you get used to working with code, the more you get used to working and you understand how code interacts with hardware, like what these CPU instructions are actually doing, how it's interacting with the system, right? With the stack, with the heap, how MMU comes into play, especially if this had like exception handling stuff. Like if you understand really what's going on based on the assembly and your understanding of, software, you can get creative in determining how you want to handle getting the unpacked code. And in this case, this unpacked stuff is pretty simple, right? Like we have this small code batch here. We have two function calls that are really small. It's not a large amount of code. So I went the route of understanding it and re-implementing it myself. Sometimes even you can actually look at the C view of code and you can actually like copy paste the actual decompilation code and use that. Of course, we didn't do that in our version because it's small enough that we don't need to. And also there's lots of garbage in here, right? There's a get last error call, which isn't even used in the function. So we can completely ignore that. But we're going to look at another method now. And that's because the point of this exercise is kind of twofold. Not only are we, using this actual malware sample as a challenge for us to analyze, we're also using it as a good target for technique practice, I guess, right? Because there's lots of interesting things that this binary does that you'll come across in other obfuscated malware. That's the benefit of analyzing such a complex and real piece of malware here. It employs garbage code, it uses packers, it uses mixing and matching of ABIs, fast call, some custom registry parameter ABI here. You've got cdecal mixed in as well. You've got garbage code. We've had things that we had to patch and identify as a waste of time. There's so many like little bits of techniques and stuff that we can dissect and use as a learning point in this binary. So we're going to now analyze this through emulation. Now, of course, you could also do it with a debugger. But when it comes to malware, the thing is, with debuggers and hypervisors, right? the idea there is you have your code, or you have your target, right? Target.exe. Now, with this live wait that we're going to do, the idea is that the target, through its natural means of running, right, at some point, it's going to unpack itself, right? I mean, the whole point of it being packed is that it's going to unpack itself and run its unpacked buffer, right? As we see by calling the unpack line and calling into its unpacked bytes. Like naturally, through its own process, it is going to unpack itself. So the whole idea about, virtualization or emulation and things like that is that the target's going to do stuff. It's going to unpack itself such that it's going to have, target. It's going to get into an unpacked state. Now, the idea here is that we can just, let me get an arrow, point that there. Okay. So the whole point of this next one is that, the target's going to unpack itself. So why don't we let it unpack itself and then we just dump the whole process, including its memory state and everything, once it's been unpacked? Now, there's a couple things here. First of all, we have to identify a condition that tells us that the target is unpacked. And that's when we dump the process. In our case, it's pretty simple, right? We know that at offset 22C6 from the start of this .text section, the start of the binary, it's going to call into the unpacked bytes. So we could simply set a breakpoint here, and when that breakpoint is hit, that means that the buffer's probably being unpacked because it's about to call into it, and we can dump the memory. Now, it's not always that simple. Sometimes you'll have targets that overwrite their own memory and stuff like that. So you have to think of how you can get creative. Now, if I'm analyzing this in a virtual machine or I've got a debugger attached and that, one way we can identify it, the fact that it's been unpacked, was, as I just mentioned, when it gets to this virtual address or this offset from the binary, right? What other ways could there be? Actually, to kind of express that creativity, I recommend maybe taking a pause for 5 minutes and thinking about, taking a look at this binary and thinking what other conditions or patterns could you use to determine that that the bytes have been unpacked. And don't think of limitations here in terms of how you could do that check in a debugger. The first step is to think about designs, right? Potential designs, potential ways that you could identify the bytes having successfully been unpacked. You don't have to worry about the implementation. Like, if I were to implement this, like if you thought of something like, well, it does these patterns. So if I found this pattern ending on this piece of code or this piece of technique or something, or this API call, then that means that the buffer's being unpacked, right? You think of the design first, and then you can think of, okay, can I actually implement this in Rindebug debugging? Or can I implement this as a debugger, as my own piece of code that attaches to the process as a debugger? You worry about the implementation after you've come up with some valid designs. Or at least that's my approach. Okay. If you haven't taken a moment yet, pause and think about it a bit, look through the binary. Otherwise, I'm going to continue and list off, an idea that came to my mind. Okay, so there's a few patterns that usually work. In this case, it doesn't particularly work for this one that I'm going to tell you, but there's others. So one such example is the use of virtual protect. So some buffers, what they'll do is when they allocate memory, they'll allocate memory to be readable and writable, not executable. And then since it's readable and writable, they can unpack the buffer, right? Because to unpack the buffer, they're just reading bytes and writing bytes. So that's fine. But when they go to execute it, they have to change it to executable, not just readable, writable. So sometimes there'll be a virtual protect after the buffer's been unpacked to change that buffer to be executable. In that case, you could write debugger code that analyzes the binary and says, if there's a piece of memory that's been allocated as readable and writable, and then it gets turned to executable, once it's turned to executable, that means that the buffer's been unpacked and dump that process memory. That's one such way. In this case, it doesn't work because the buffer is actually allocated, or rather changed before it's unpacked, to 0x40. And 0x40 is readable, writable, and executable. It's all three. Now, readable, writable, and executable means that it doesn't have to change the protection of the buffer after it's unpacked it, because it's already executable and readable, writable. But the problem with this is that if you do any, EDRs and antiviruses and that, typically, maybe they're not as strict in lots of organizations, because lots of organizations actually use dodgy code that will make readable, writable, executable memory. But typically that's a flag, right? Like a, hey, I'm potentially malicious type flag. Because really the only reason why you need code that's readable, writable, and executable is if you're dynamically creating code to be called. Now, there are some legit processes that will do this, right? JITs, which is just-in-time engines that live in your browsers and in some other pieces of code. They will do that. But outside of those types of code, your average process is not going to have a legitimate case for doing that. So that can be a potential red flag. But there are other patterns going on here that we can leverage. That is actually very similar to the one I just said. And that is, well, okay, what if we have a buffer that's allocated and it gets written to, and then it gets executed? At the point that it's been executed, we can dump process memory then, right? Because even though this buffer is marked as readable, writable, and executable, it's only actually executed once it's been unpacked. So you can say, if you have a buffer and it's being written to or read from, wait until that buffer address is being executed. Once it's been executed, then dump memory. That would work, right? Because we would identify that this buffer is only actually executed once it's been unpacked. So the question then is, can we identify a buffer that's dynamically allocated and marked readable, writable, and then identify when it's been executed? In this case, we can. So local alloc, right? That's just a function that lives in kernel 32. We can hook local alloc, right? We can hook it. We can attach a debugger to this process and just set a breakpoint on local alloc. And once we break into local alloc, we can note down the buffer size, which is one of the parameters. And when local alloc returns, we can note down the address that was returned. Now, at this point, we know the address of the buffer and we know its size. And we're a debugger attached to this process, so we can modify the process state. What we can do then is we can actually mark that buffer as just readable and writable. And we can also hook virtual protect, so that if virtual protect is called to change the byte to executable, we can actually override the virtual protect call to make sure that the buffer does not become executable, right? As a debugger, we can put a breakpoint on virtual protect and we can check the address parameter. And if the address belongs to that buffer that was allocated, we can say, no, it's not going to be executable. We can change the new protect value to make it only readable and writable. That would allow this piece of code to go on and unpack the buffer perfectly fine. But when this piece of code goes to execute that buffer, since we prevented virtual protect from making it executable, this call into the buffer is going to raise a exception. It's going to raise a page fault because the CPU will see that you're trying to execute non-executable memory, only readable, writable memory. And as a debugger, we're going to receive that exception. And at that point in time, we know that the target has tried to execute the buffer so that the bytes in that buffer are likely unpacked. We can then dump that process memory, right? So to kind of cap that up, debugger, attached to process, hook memory allocations. In this case, local alloc, but we could actually hook all memory allocations if we want. Virtual protect on a logged memory address from above. Then we can ensure it doesn't get marked as executable. Okay, so us as a debugger can attach to a process. We can hook or set breakpoints on memory allocations and log them. We can note if virtual protect has been called on any of the logged memory addresses by hooking virtual protect and checking the address. Ensure it doesn't get marked as executable, which we can do by modifying the parameter such that it removes the executable flag. Now, page fault exception on address being executed, dump memory. Okay. So, of course, there's some little things we would have to handle here as well. For example, we're hooking allocations. We should also hook freeing of those allocations so we don't have stale logs, right? Because if a memory is allocated and then freed, we don't really care about it. We can remove it. Of course, there's probably some sneaky techniques in the code that could be used by our target, such as actually having a use after free that it leverages to get past our logging, but we don't have to worry about that in this case. This is just a little example of how you can think of a solution that might work. And in this case, this likely would work. You attach to the process, hook allocations, hook virtual protect. If it's being called on one of your allocations that you logged earlier, remove the executable flag if it exists in that virtual protect call. If you get a page fault exception because an address is being executed that's not executable, then that's probably the target trying to execute its unpacked code. So dump the process memory at that point, and then you can load that in to Binary Ninja or Gudra and analyze it. Right. And this design here is pretty generic because it doesn't do anything based on hard-coded offsets or addresses. It does it on patterns. We're hooking Windows API calls, and that's it. We're not attaching breakpoints to offsets in the code, such as, this offset 22C6. So theoretically, our technique here can work on multiple malware samples and not just this particular one. It's a pretty generic technique. So that's pretty cool how we can actually think through some of the designs that we could use to identify when code has been unpacked. And then you can write some code, write your own debugger process, or use a Windows debugger or something like that to try it out. Now, when I say write your own debugging code, well, I'm not sure how many people have experience with this, but you know that Windows has debuggers, right? Windows has, Rindebug, which is the GUI debugger, and there's documentation for it. Windows also has CDB. CDB, actually, there's kind of a few listed here, right? So I'm not sure if it dives into each of them, But CDB is the console debugger. So it's the command line debugger. It doesn't have a nice GUI. It just gives you the command line. So it's like a minimal debugger. NTSD, I think, is like an old version of that or something. I haven't used it much. Rendebug is like the Windows debugger. It's like CDB, but it's got a nice GUI. KD is a kernel debugger, and you can do kernel debugging from the command line. I believe KD is the kernel version of CDB, but Rendebug, the GUI version, also supports kernel debugging. However, you can write your own debugger. You don't need to use these actual debuggers, right? There's APIs in Windows to attach to a different process as a debugger. And they're actually listed under debugging functions here. Let's see. Here you go. Debug active process, for example. You give it a process ID, and it'll attach your process to that target process and act as a debugger. And you can stop debugging it with debug active process stop. And there's information here on how you can leverage. You can create debugging events. You can read and write memory, of course, which means you can also hook that, so you can like attach to a process, or you can launch a process as suspended, attach to it, and then resume it. And then you can, hook APIs in that process by putting breakpoints on certain bits of it. You could also actually use the hooking APIs in Windows that are implemented via what's that hook library called? I use it actually a lot. And I'm blanking. There you go, Microsoft Detours. That's what I was looking for. I should have just rented my own GitHub because I use this a lot. Microsoft Detours is a GitHub package by Microsoft, and it provides you APIs that you can use to hook functions in other pieces of code. So you can hook virtual protect. You can hook whatever you want this way without using breakpoints. Of course, breakpoints would also work. Cool. Well, that said, we're going to actually do this via emulation instead. Emulation is a bit different. So, with this way, if we're using a debugger or running it in a VM, the target is actually executing code on the CPU, right? It's executing on your hardware. Even if it's in a virtual machine or whatnot, it's your actual CPU that's executing the target. With emulation, it's a bit different, because with an emulator, the CPU state, the hardware state are actually software. It's variables. You'd have like a struct CPU, and in there you'd have like, the registers, REX, which is like a register type, and blah, 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 blah. And then the registers type would be like, struct register. That would have like, that'd be like a union or something, where you'd have, the full 60. Well, actually, Rex would be a, say, general 64 register, right? Because there's actually different types of registers, like system registers, like CR3 and that. But Rex could be a general 64 register. And a general 64 register could be like a union of like, it would have the as U64, which would be a U64 type. And this would typically be, like Rex, RDX, RCX, right? But then you'd have a U32 version, which would be like low 32, which could be like, ECX or, EDX, whatever. And then you'd have like low 16, which would be like CL or DL. And then you'd have like high 16, which is like CX, DX. The whole point of this, just to give you an example, is that emulators, when they execute the target, they're actually interpreting the target and emulating it, and the CPU state for that is stored in software. It's just a CPU structure, right? Every register is defined properly as its own types, and its entire state is just software. So if you have the target, right, say this is our target.exe, and this is our, emulator. Our emulator would like read some bytes, read some bytes after it's passed it as like a PE format or whatever. And, say that byte is 0x. Let me find it. Here's the online assembler, right? Say it's doing comp ESI 0x20. Those bytes are 83FE20. So say it reads bytes and it gets these bytes, 83FE20, right? It interprets that as an instruction, which in this case is comp ESI with 20. So it interprets it as comp ESI 0x20. And when it goes to execute this, it doesn't execute that actual instruction on hardware, right? Instead, it'll have a compare handler, right? Some compare handler function. And this compare handler function would be like, okay, get CPU state ESI, and say this is actually reg and this is value, which is the 0x20. It gets the CPU state of that reg, which in this case is ESI, and it'll do, if ESI equals to 0x20, blah, 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 blah. Actually, I'll say like P1, which is parameter 1, equals to CPU state and that reg, which is, this reg here. And then it'll be like, well, if P1 equals to 0x20, do something. If it's less than it, do something. If it's greater than it, do something. Realistically, you probably check it bit by bit and set the CPU flags in that. But the main point here is that it's not actually executing compare ESI 20, right? It's reading bytes from the target, decoding it to find out what instruction it represents, and then there'll be some function in the emulator code that will handle that assembly code. It'll handle comparisons between a 32-bit register and a hard-coded value, and then that function will, get the actual values it's comparing from its CPU state structure, and it'll do the comparison, set the flags in the CPU state as required and stuff. And then once it's finished emulating it and updating the state of the CPU and maybe updating the state of the memory, because there'll be a memory state structure as well, then it'll return to the main decode loop here. It'll read some more bytes from the target. It'll interpret that as whatever instruction the next bytes are, and handle it. It's all emulation. Now, emulation is slower because naturally, instead of just executing the instruction, you're going through, other pieces of code in the emulator that handles that instruction, right? And there is a benefit to this though, and that is the entire CPU state, memory state, hardware state is all just software in your emulator process. So it's very easy to see what's going on, and it's very easy to manipulate and change hardware behavior. For example, if I want to see what all the register state is in CPU state, I want to see what all the registers contain, I can just dump out this structure and be done with it. If I want to know when a particular address has been executed, right, like with the debugger, you set a breakpoint. With an emulator, now say quickly with breakpoints, right? You have hardware or software. Now, hardware breakpoints are limited. Software breakpoints are unlimited, but software breakpoints actually modify code, right? If you have a piece of code that's like inc edx nop, I'll just say inc edx jump, I don't know, move rcx 0x20, sub rsp 0x32. If you have code like this and you set a software BP at the start of it, you actually end up overriding like inc edx with just int3. And then the debugger, and then, when the CPU executes int3, it'll go to the debugger, and then the debugger can replace int3 with the original instruction, which I already forgot what it was, inc edx, right? But since using a software breakpoint, you're modifying memory, there's actually a chance that the target can verify if its memory has been changed. It can take a hash of itself and compare that over time to see if it's changed. And if the hash has changed, it's because the instructions have changed, which likely tells the target that there's been a software breakpoint inserted in that function. And then it knows that it's being, watched or something, and it can change its behavior. There's also, and with a hardware BP, what that does is instead of modifying, I think it was that, instead of it modifying software, it sets a register. There's register debuggers. I think they're called like DR0, DR1, something like that. And there's CPU registers. They're debug registers. And they contain addresses that, like, when executed, the CPU will raise a breakpoint to the debugger. Now, there's a couple problems with this as well. One is that when you're live debugging a target like this, there are a few API calls and a few things that the target can do to identify that it's being debugged. Additionally, you have a limited number of debugging CPU registers. So if you want to put a hardware debugger on like 20 functions or 20 places in code, you likely do not have enough CPU registers to handle that. You'd only be able to do a handful. With an emulator, right, every address that's being executed is just in the CPU struct, right? You have the CPU struct, and that would have like RIP or just the PC register, which may not always be RIP, right? If it goes into 32-bit mode, it'll be EIP. It can also go to like 16-bit mode, real mode, and things like that. But, either way, the point is that the program counter, the register of the CPU that holds the instruction to execute, will be a part of the CPU struct. And you can simply, the emulator will always go through a process where it reads bytes from that register to get the next opcodes to execute. You could simply have a extra bit of code here that before this, this reads bytes from, RIP or whatever. You could actually, let me extend that out a bit. Before it actually reads those bytes, you can add a little detour in the middle here. That says, check for BP RIP or something like that, right? Now, your emulator will just have a whole bunch of breakpoints in an array. You'd have like breakpoints array. And whenever you add a breakpoint, you just do like breakpoints dot push BP address. Right? So then when the emulator, as it's executing the target, before it actually reads bytes and handles the instruction to emulate, it'll check that address to see if there's been a breakpoint registered for it. If there has been, then it can go on and call your breakpoint handler for that address, and you can handle that breakpoint. Now you can see this way, it's not like live debugging. You're not using a software BP to actually modify target memory at all. Target memory does not change. It's like using a hardware BP, but you're not limited by CPU registers because you can just have as many breakpoints as you want in your array, right? So this way, you could have 1,000 breakpoints if you want, and you'd be fine. That's some of the benefits that emulators give you. Now that we've kind of discussed this and we've looked through some of the approaches and talked about the design, in the next video, we're going to actually leverage emulation code to dump out the memory dump.